Okay, good evening, students. My apologies for the delayed start because we were facing some technical issue. Hopefully, now it will get connected properly. Uh, so, again, I saw some messages that people have been waiting for some time. So, again, I apologize for the delay. And there will be some lag between what I see and what you get. So I am right now seeing some queries which were already posted. What I will do is I will first try to answer those, and then we can take some queries from the live chat. So hopefully that is okay. So first query is from Abhishek, and he has asked a couple of questions. The first question is, whenever dead time is higher in measure transfer function, that is delay in measurement, would you go for a PID controller? And yeah, so what I would say is, so far up to week 4, we have only looked at uh, what are the controllers. We have not yet looked at what would be the when do we select which type of a controller. So controller selection is going to come. It is not just dependent on the delay in the system, uh, but we'll be looking at controller selection, especially the PID controller selection in week 6. But just to give you a very short answer, what I will say is, typically when the system is slow and we want to make sure that there should not be any offset, we try to go for a PID controller. At least we add the derivative action. But if the dead time is significant, then even PID controller performance would not be that great. So we go for some sort of advanced controller. It will be a traditional advanced controller like Smith predictor or Smith corrector, or we can even go with a model based controller like MPC. So all those things we'll discuss later on. So right now I will just leave it up to that. But we'll be talking about when do we select PI or PID controller in week 6. His second question is the on-off controller. Let's say we have an on-off controller and we are using some quenching wall which will open at 75% and close at which will open at 75 degrees Celsius and close at 40 degrees Celsius. That means the dead band is going to be 35. So can we call it as an offset? So now it's little I don't know whether you are attending this live, Abhishek, but what I would say is the offset is defined from a set point. So when you are saying that the wall opens at 75 degrees Celsius and closes at 40 degrees Celsius, but you have not mentioned what is the desired temperature what we are looking at. If it is in the middle, then obviously the offset will be half of 35, which will be 17.5. But if the set point is somewhere like 70 degrees or 75 degrees, then the offset can be as high as 35. So I hope that answers your question. The next question is from Prant, and his question is, when do we use PPI or PID controller selection of this controller? So as I mentioned earlier, we will be talking about this PPI and PID controller selection in detail in week 6. Especially we'll look at it even from the control variable perspective, like if we have flow controller, what kind of controller we use, if it's a level controller, whether it should be PPI or PID. So all those things will be discussed. So I think you can wait for some time. And there is a one more last question from online or the offline query, which is it always that a system is 5 the system always takes 5 times to reach the steady state when we go for a first order system when it goes to a new steady state? uh, so the answer is, if it's a first order system, you give a set point. So as long as that set point is a step set point that you just changed it and kept it constant, then we have seen through mathematical derivation that the response of the system is given by akp into 1 minus e raised to minus t over tau. So in order for this system to reach AKP, it is gonna take e raised to t minus t over tau has to be equal to has to go to 0, and that will go to 0 around when t is equal to 5 tau. So that is why typically we say that 5 times the system, if it's a first order system, we'll say 5 times the time constant it takes to reach the steady state. A lot of times we also take 95% response, which comes at around 3 tau also. So these are just rough estimates. And then if the set point does not change by a step change, then it may not take 5 tau. So let's say if the step, there is a pulse in the step, in the set point, then there are 2 steps. So in that case, the overall time will be 5 tau after the second instance of the pulse. So now I see that there are some questions in the live chat. So I'll take them one by one. The first question is by Ravi. Good evening, Ravi. He is asking me to explain about poles and zeros. So poles and zeros are defined. So I think in the videos you might have seen, if we have a transfer function, if we take a general rational transfer function, we can always write it as some polynomial in S in the numerator and some polynomial in the denominator. So the roots of these polynomials give you poles and zeros. So if I take, so let's say if my transfer function in a general form is gs equal to ns over ds, then ns equal to 0, that equation will give me the zeros of the system, and ds equal to 0 will give me the poles of the system. Now let me give you some significance of each of those. So the easier one to understand is poles. So that those are obtained when we take the denominator polynomial equal to 0. So these are sort of the dynamic modes of the system. So the dynamic mode can be a constant, the dynamic mode can be a linear change, the dynamic mode can be an exponential decay. So all, if your response, how many dynamic modes can it have? So that is given by the poles of the system. So let us take an example. So if I say my system's transfer function is 1 over s minus 1 times s minus 2. So the denominator ds polynomial is now s minus 1 into s minus 2, and the two poles of the system are 1 and 2. So what I mean by dynamic modes of the system is, if I try to inverse Laplace this particular system, and let's say I'm looking at a step response, then the solution of this will involve e raised to power t and e raised to power 2t. So those 1 e raised to power 1t and e raised to power 2t, those are coming from the poles. So here the poles were positive. So the dynamic modes of the system are going to be uh, positive exponentials, e raised to t and e raised to 2t. Both of those will go to infinity as time goes to infinity. So the poles of the system are very useful in identifying whether the system is going to reach a new steady state or it is going to go into instability. So that is why we require the poles. Now zeros are zeros tell you the relative contribution of these dynamic modes. So let us say in the transfer function which I told you, 1 over s minus 1, s minus 2, there is no 0, because the numerator is just a constant, it is not function of s. But if I put something in the numerator, let us say s plus 1, So in that case, the zero of the system is going to be at -1. So now what impact it will have? We have, I think we have seen it in the video. Let me just check. We must have seen it in the uh, one of the videos in week 3 of called as numerator dynamics. So zeros give you numerator dynamics in the sense that even if the two systems have the same poles, that means the same dynamic modes, their relative contribution can change. And when that relative contribution changes, we can even get a first order type response from a second order system, or we can even get inverse response, we can get overshoot. So all those sort of things will come in when we have something in the numerator. If the numerator or the zero is at 0, that means the numerator polynomial is simply s. Let's say your transfer function is s over s plus 1, s plus 2. So in that case, the 0 is s equal to 0, that means z equal to 0. So that system will always go to origin. So the final value of that system will become 0. So I hope, Ravi, that was more, that was useful for you. You can type in the chat box if that answered your question. Let me see the next question. How do we, next question is from Sheena. How do we find the rise time? So now rise time is typically defined for a underdamped system. Let me just clarify what is rise time. So rise time is the time taken by the system to reach the rise time is the time taken by the system to reach the set point for the first time, or the final value for the first time. So if you recall what is the response of an underdamped system, it starts, let's say, with from the origin, it goes to the set point, goes above it, then comes back, it goes as a decaying oscillations, and eventually it reaches the set point. So by the first time it reaches the first time it reaches the set point, that is known as the rise time. Now how do you find the rise time? I think there is an expression for it. Let me check it. Mm. Okay, so there is no direct expression, or at least the reported expression. But let me see if this works. Let me try to share something. And if you are able to see this, then you will be able to see that this is the rise time by the time the response reaches the set point for the first time. And if you see it from this graph, it is strongly dependent on the damping coefficient. If your system is less damped, or that means under damped, the zeta is very small compared to 1, then the rise time will be faster. That means the system will reach the set point very fast, but it will not stay there. It will have long oscillations or the multiple oscillations. The more system moves towards critically damped or over damped system, if I go in this particular direction, if the increasing damping coefficient, then you will see that the rise time slowly reduces, and so are the oscillations. The oscillations will also reduce. So it is dependent on the damping coefficient. if you are simply comparing two systems, then you can compare them. The rise time you can qualitatively compare, in the sense that if the one of the system has a higher damping coefficient, then it will have higher rise time also. So I hope that answers your question. Let me see what is the next one. Is reflux drum not considered in the stages of the distillation column and considered as a separate stage? So reflux drum would be considered as one of the stage, uh, in the sense that see, what we are looking at is the number of dynamical systems or the dynamic variables which come in between the input and the output. So if you see if you try to look at write down the equations for distillation column, the reflux drum will also have an equation that dxd over dt will be equal to v times uh, y1 minus xd. So this itself is a first order system. So reflux drum itself is a first order system. So it is connected with a distillation column which would have some n number of stages, so which will be an nth order system. So obviously it will be considered as a dynamic stage. Now, when you talk about separation stage, it is not a separation stage because no separation happens in the reflux drum. But from a dynamic perspective, it will be considered as a stage. So I think that probably was the question by Saurabh. The next question is a little more on a professional side rather than the course which we are taking. What is the scope after having a specialization in process control? So process control is a very dynamic field, in the sense that every operating plant has to have a process control system. You can have a process which can get obsolete after some years. Let's say a catalyst gets replaced or something, so that expertise can lose. But in terms of the control, any plant which comes in, whether you have a new plant or an old plant, it will always have to be operated, and for operating that you will need a control system. So if anyone is an expert in control system, obviously his role is always going to be there. If you are operating a plant, the knowledge of process control is very useful, because that will keep you up to date in terms of maintaining your targets for the plant. If you are even looking at specialization only in process control, like the companies which give you advanced controllers, or the controller companies like ABB or Honeywell, which supply control systems for a chemical plant, even there you will see that then your role is not only limited to the control of chemical system. You can even be looking at control of mechanical systems, control of metallurgical system. So in a sense, the scope for process control is very wide, and if you want to pursue it, uh, my best wishes for you. The only thing is you have to be very good at maths, because a lot of times there will be equations and you will have to try to solve them and then debug them. The next question is pure capacitive process self-regulatory, and how? So purely capacitive process is not self-regulatory. So when I say self-regulatory means if I give a disturbance, then after some time, if I don't take any action, the system will stabilize somewhere. So that is known as a self-regulatory system. If it comes back to its original point, then it's good. But typically a system will not come back to its original point. It will go to some other point. When we say purely capacitive process, let's take a simple example of a tank, and where input and output both are independent. So if I close the input and let the output be whatever, then obviously after some time the tank will drain. So that means it is not regulating itself. Similarly, if I had done the other way around, closed the outlet and kept the inlet on, after some time the level in the tank would have overflown. So purely capacitive process is not self-regulatory, it's in fact unstable, which we'll be talking about in week 5. Mm, Then the next question is on-off controller with band 0. What is significance of this? So that is more from a um, theoretical point of view, that you typically want your system to remain at the steady state. So you are taking action whenever there is an error. So if you try, that is more from a comparison to PPI and PID controller. So on-off controller with deadband of 0, that means that the moment error becomes positive, you take one action, and the moment error, then the error will switch sign, and then you take another action. So theoretically, it will try to keep the system at the set point, but it will come at a very big cost. It will come at the cost that the wall will continuously be going between on and off, and then the life of the wall will be very low. So therefore, in reality, you generally try to put some dead band so that the wall does not move on between on and off very frequently. That is known as chattering of the wall. So I think that is clear. The next question is, do we get an overshoot in on-off system as we get deviation from the set value? So now again, I don't know what you mean by overshoot, because uh, typically when you have an on-off controller, you will always have the system will never be at the steady state. It will always go some value above it, and it will always remain within a band around the steady state. So in a way, it will always have an overshoot. The next question is, what is override control strategy in process control? So now we'll be talking about override control in, let me see, in week 7. So override control strategy, as you have asked the question, let me just say something. So the controllers which we have seen so far, they always have one input and one output, right? Let's say PPI, PID controller, or in any system, what we have seen so far is one input, one output. But what if you have two control variables, but only one input? So how do we go about controlling it? And in reality, that's typically the case. You have multiple things which you want to control, but you have very few inputs available for control. So in that case, what you do is you typically write a logic, that is one of that logic is override control, such that under normal circumstances, the pairing will be between input and output 1, and only under some safety related constraints, or typically that's related to the safety related constraints, the pairing will move from input to output 2. So in some sense, you are able to control outputs 1 and 2 within a certain range. So we'll be talking about this in more detail when we talk about override control. So again, I'll say hold on for some time. But that is a control strategy which is used when you have more control objectives and less inputs. The next question is from Ravi. When you converted time transfer function to Laplace transfer function to find the value of P controller, you multiplied S to GS. I'm not sure what you are asking, because I'm not able to. I will not be able to see the video right now. Uh, so I think this question you can post it as a discussion forum, and then we'll be able to see exactly what location of the video you are talking about. But Laplace transfer of a P controller is simply Kc, because it's a constant. And if you are trying to take the response of the system, that means step response. So when you take a step response, then 1 over s will come in as 1 over, because it's a unit, let's say if a unit step, then I'll have 1 over s coming as a transfer function. And if I'm looking at the final value, So a lot of times I look at where does the response settle. So if you're looking at the final value, then I have to use the final value theorem. In order to use the final value theorem, the final value theorem says that limit of yt as t tends to infinity is equal to limit of s times ys when s tends to 0. So that's probably why that s is coming from. Uh, so maybe you can revisit that video, and if you are still not clarified, then you can raise a discussion forum on that. The next question is, do we need to mug up the expressions for overshoot? No, no, no. So typically what I say is there is no need to mug up anything. All these, so if the expression is there, if even later on when we are talking about controller tuning, so which will be coming in week 6, then there will be a lot of formulas. So those formulas I will be giving in the final exam. So whatever you will be tested is for the knowledge or which can be easily derived. You will not be tested for your memory. For model, we can analyze the process and measurement and control while by differential equation. But for real industrial case, we do not know the equation. How can we analyze? So again, this is a question for something which we are going to see later on. Let me just point out when we'll be seeing that. We'll be seeing this again in week 6. So what I will say is again, I will not disappoint it. I will not disappoint you. I will just give you some answer, which is which we are going to discuss later on. So what we typically do is known as a step testing. So in a real plant, we do not know, or we do not even want to write equations for distillation column, equation for control wall, equation for sensor. So what we typically do is we give a step change in the input. We give a step change in the input, and we record how the output looks like. How the output looks like, and then from that we can see whether it is a first order process, which typically it will never be, or a second order system. Typically it's an nth order system. So what we do is we convert it into a first order plus dead time, like we have seen in I think week 3. Yes, in week 3 we have looked at how do we convert a higher order system into uh, first order plus dead time. So that particular method is known as step testing. So that is a very basic thing. That's how we know what is the transfer function of a real process. But we'll talk more about this in the week 6. Next question is from lecture 25. Again, I don't know what is exactly lecture 25. How PID controller is going to how PID controller is going to control integral action. So I'm not sure what this question is. Uh, so PID controller has all three components. So it has a proportional control element, it has integral element, and it has derivative element. So proportional element will just give you the initial kick, the speed of the response. The integral action will ensure that you get offset free response, and the derivative action will try to speed up the response of the system by doing some basic prediction. What is the advantage of mechatronics over process control? I don't see that as scope of this particular course. Explain a bit more about reset windup. Okay, so reset windup is a phenomena which occurs when you have integral uh, when you have a lot of integral action in the system, and the system is not able to do uh, the job because the control wall is getting saturated. So let me see if okay. So let us say uh, you have a system, and it is badly tuned, in the sense that you are penalizing your integral action is much stronger compared to the proportional action, and because of that, what will happen is, as you have some amount of error in your system, it will keep on integrating, and then obviously the output, let me just share this screen. Okay, so what you will see is this particular element, if I keep 1 over tau I to be high, just hypothetically, in reality this will also happen. So in that case, what's going to happen is, this is going to be much stronger compared to this particular term, and your ut will be very high. So ut, mathematically it can go from any value, but in reality ut will typically be a wall. So wall opening. So wall opening can go between 0 to 100%. So if I badly tune a controller or select by wrong values of these, then even for small error or some error, the ut will become 100%. Now after that, uh, the controller, the error will still not be gone. So in that case, it will keep on integrating this. So it will keep on increasing the mathematical value of the right hand side here of this equation. Will go beyond like 100, 200, 4000. Practically, the wall can open only up to 100%. So the system will only see 100%. So unnecessarily, all this will get accumulated as an integrator. So this integrated term will go to a very high value. Now, after some time, that having that wall 100% open, the system will start responding in the correct direction, and then the error will go into the negative sign. So now, this error proportional term will automatically become negative the moment y goes above the set point. But the integral action has already become so much positive that even if the next few errors are negative, the overall integral term will still be highly positive, and the wall will still not close, because the wall is a combination of instantaneous contribution p controller and the integral action. So unless that entire integral action is cancelled, the wall will not move from 100% open. So this causes very slow response of the system. So that is typically known as a integral windup or a reset windup. So what typically is done is anti-reset windup logic, which is all incorporated in any PI controller. So what it says is, the moment you hit the constraint that the wall is saturated, let us say the value calculated by the right hand side of this becomes 100%, that the wall cannot open beyond that. After that, any error which comes in, it will not get integrated. So because of that, this integral term will stay at its own value, and the moment this error becomes negative, and the entire this expression will now start moving you in the negative direction, that it will become 99, 95, and then again the integral action will be on. So the integral action will only be on when the value of ut calculated by the expression is between 0 to 100%. This is known as anti-reset windup. So this increases the speed of the response. So I hope uh, that helped you. The next question is, when we use initial value and final value theorem in process control. So these are used to find the initials and final values of the response, as the name suggests. So let us say if you have put in a controller, then obviously what you would want is, as a long-term response of the system, what is the final value of the response when I put in this controller. So in that case, we'll use the final value theorem. Sometimes we are interested in the moment the controller is switched on, what happens to the system system. Does the system require a much bigger change in the input? So typically when we want to see how the input changes, that time we use the initial value theorem, because we want to see how the initial value is going to change. So those are the places when we use initial and final value theorem, because by combining initial response and final response, you can predict how the system is going to respond. You don't need to take the entire Laplace inverse and solve the system. So these two theorems, initial and final value theorem, help you sort of predict how the system is going to respond. I think that's what we have been using in the course also. If we convert time function to Laplace, it will be GS only, right? Laplace of ft will be S. Yeah, so g of t, if I take Laplace, it will be g of s. Laplace of derivative of f of t is going to be s times fs minus f of 0. That's correct. Typically what we have is our system is, we assume the system to be at steady state initially, and all our variables are derivations, so f of 0 typically becomes 0. And that is why our transfer function or the Laplace of derivative typically is s times f of s. So Ravi, I guess I will have to go through the video and see what has happened. Maybe there is a typo. So it will be better if you point it out on the discussion forum exactly what has happened, and then me and my TAs can look at it. How PID controller is going to control integral action. So what will integral action do? Basically, what is the role of integral action? So the role of integral action is to make sure that you get offset free response. See, again, let me share something. So here you see. So this is the equation for a PID controller. The input U depends on what is the instantaneous error, what is the integral of error, and what is the derivative of the error. So now let us say this ut has to become constant, because only when the input becomes constant your system will become steady state. So in order for this to remain at steady state, your error has to go to 0. Only if error is 0 and the integral of error, all the past errors, that is also 0, then the system will remain at a steady state. So typically that helps you in terms of achieving the offset free response. If your y set is not equal to y, then your integral contribution will always keep on going. Let us say if your output is constant but it is not equal to the set point, so then this will have a constant value. Even the derivative will be constant, because derivative will be 0, because y set minus y is constant. So even if you have an offset, a PD controller would reach a steady state. But the moment you have an integral action and there is a constant error, it will keep on getting integrated and you will not remain constant. The only way you will remain constant is when error goes to 0. So that is the purpose of having an integral action in your controller. Without integral action, you will not get offset free response, whether it is a PI controller or a PID controller. Why does slope of YST have a slope 0 at equal to 0 for a second order system? So the next question is by Sheena. So she is asking slope of, I don't think it is ys, it has to be y of t. So y of t versus t, only if it's a first order process. Now I'm talking about this processes without any numerator dynamics, or the overall order of the system is 1, only then the initial slope will be non-zero. If you have a second order system, third order system, or any nth order system, the initial slope will be 0. The simple physical reason behind this is you can consider or physically, or let me say more from a understanding perspective, see that any second or higher order system is a combination of multiple things. So the moment I give some change in the input, the immediate effect will be felt by the first system. The second system is driven by the output of the first. So only when the output of the first changes, the second system will have an input change, and then accordingly it will have its own output change. So therefore, any second or third or higher order system, it will always have a delay in terms of starting its response. So therefore, the initial slope will always be zero if the system is not first order. Now, this explanation is for a system without numerator dynamics. The moment you have something in the numerator, the overall order of the system changes, because then the overall order is the polynomial, the degree of denominator minus degree of numerator. So, if your numerator is first order and the denominator is second order, the net order will again be 1 and the initial slope will be non-zero. The example of that will be a transfer function like s plus 1 over s plus 2 times s plus 3. This is not this is a second order system with first order numerator dynamics. So here also the initial slope will not be zero. As a PID controller, sorry, as AS, PID controller can give kick to the process because it has also P term in the equation. When yes, so that proportional kick I have said, I explained it after P control action, but I don't know whether I mentioned it in the video or not. But the moment your controller has a P action, that proportional kick will be there, whether it's a P controller, PI controller, or a PID controller. So that will be there for all the three controllers. The next question is how to reject that error which is generated by integral action if our output will not be stable, as the error will have constantly add up in. So that is why we have that anti-reset windup. So if your system, if your input is already saturated, then there is no point in terms of penalizing the controller for not doing, because the controller is already doing whatever best it can. So anti-reset windup just ensures that the integral action is turned off the moment your controllability is lost. What I mean by that is the control wall has saturated. So that error gets rejected in the sense that your wall is completely open. So we hope that that wall had reached saturation because the controller was badly tuned. If the controller was properly tuned and the system response, let's say your system is such that in order, if you have asked for a set point change which is not physically realizable, so in that case, again you will see a similar response that the control wall will get saturated, and in that case the system will not be able to reject that disturbance, reject that error, because the system cannot handle that. It's not in the capacity of the system to have that kind of a set point change. So I guess that was clear. Sir, will I be wrong if I say that the transfer lag is due to the narrowness of the pipe connecting two tanks, and that is nearly eliminated if we increase the diameter? So now you are talking more about the physical systems. So let us say if you have two systems and they are connected by a long pipe. So then we know that pipe, we can consider it as a PFR. So the PFR is more like a delay system. Whatever goes in, after some time it will come out. So that delay, the transport lag will come in as a part of the pipe. So now, what is the time constant? What is the delay that is equivalent to the time constant? You have seen the residence time distribution in your reaction engineering. I hope so. So in that case, you might have seen that the residence time distribution for a PFR is simply that whatever goes in, it comes back after tau. So tau is V by F. So if your diameter is high, and if we are assuming that the flow rate is constant, so So what's going to happen is V by F. So I don't think it is gonna depend on the diameter, because V by F is going to be V will be equal to area times length, and flow rate will be Q times velocity times the area. So you'll have to figure out what's going to happen to the tau of that reactor. If you have the same flow rate, but if your volume increases, then obviously the transfer lag will increase. The next question is, in Nyquist plot, if curve touches -1, 0, is it stable? So in Nyquist, the condition is that -1, 0, if it circles -1, 0, it is unstable. Uh, so typically when it touches, that is typically the marginal stability, we call it. That's the point at which the stability will move from stability to instability. So you could not understand the explanation for zero slope for a second order system, although I know there is transfer lag and the slope is going to decrease. So how do I explain? See, you might have seen dominoes, right? Dominoes as in those small blocks, and then you connect them. And when you tip one of the domino, then slowly, one by one, each of those dominoes will keep falling. So the moment you touch the first one, do all of the rest fall at the same time? No, right? The effect is cascading. The first one immediately falls, then it affects the second one, then the second one falls, and then slowly the all the rest of the ones. So that is exactly what's happening. The moment you give a change, the first order process is like the first domino. So it will immediately show response. Therefore, the slope is non-zero. Second order system is like the second domino. The first is the first one will fall. Only when it hits the second one, then the second one will fall. That is why the second order system will have a will have a zero slope. So I hope that. The next question is, okay, I got it. Thank you so much. Okay. So I think these are all the questions so far. Are there any more questions? I hope you are liking the course. I have tried to make it more, what do you say, general, in the sense that I'm not sticking to any particular book. These are mostly from my personal experience in teaching this course to industry as well as academia, and my industrial experience running a plant. So I hope you are enjoying the course, and uh, more interesting material is going to come up in the later half of the course, because so far we have just developed a foundation. The more we will be moving toward more realistic systems as we go into week 6, 7, and 8. Some of the questions were tuned from there, like override control, switch, split range control. So all those things will come up, and then you will see how that really impacts the actual operation of the process. Oh. Can you share how life at University of Minnesota is like? So it's very good. It's so typically what I would say is, when you go to study in the US, the best thing you find is your peers are not are very different. So let us say in the class of 40, you will have people from 12 to 13 different nationalities. So somebody might be Japanese, somebody might be Chinese, Taiwanese, European, American, South American. So even in my group, which had only 7 or 8 students in my PhD group, we had like almost 7 to 8 nationalities represented. So you get to see a lot of different perspectives. So people have different cultures, people have different views, things, looking at systems. How do you see different angles of looking at the same thing? So that way, it just broadens your perspective. So that's one takeaway I would say, not just University of Minnesota, but in general, any international university if you go to, that sort of gives you a much broader perspective of looking at things. So far, all your peers have gone through the same type of education system, same sort of upbringing. So your way of looking at things typically are very similar. So that gives you a much bigger viewpoint. That's what I would say, other than all the things. Next question is, in second order process with first order numerator dynamics, can we have overshoot with oscillation? So you cannot have overshoot with oscillation. What you would typically have an overshoot and it will come back. So because the dynamic modes are now, again, let me correct myself. You have made a very general question. So second order process, if the denominator itself is underdamped, so if your poles are complex, in that case, irrespective of whether you have numerator dynamics or not, you will have oscillation and you will have overshoot. So, Saurabh, if your question is that the poles are real and the numerator dynamics are first order, in that case, you will not have oscillation. But if your poles are complex, then you will have oscillation irrespective of numerator dynamics. Why overshoot will happen if zero is closer to origin than pole? So now that is more from a mathematical perspective. What has happened? Yeah. So that is more so I'm answering the question, why overshoot will happen if zero is closer to origin than pole. So that is more from a mathematical perspective, in the sense that in that case the contributions are such that one mode moves it higher. The two contributions are such that they add up and then you get a value higher than the final value. But I don't see there is any physical significance to it. It's more like if those conditions are satisfied, then the value you get is higher. So I don't have a very clear-cut answer to this, but it's more of a mathematical reasoning to it rather than a physical reasoning. So if that was the last question, I'll just wait for a couple of minutes. Yes, the power grids are back now. And is this course useful for food technology students? See, in a sense that process control is required for any process. So food processing itself requires all these processes would have some control system. So I would say it is useful. So when I was teaching this course, when I was a faculty at ICT Mumbai, I have taught this course to food technology students also. Control valve fail-safe position depends on process. When we are to implement controller, reverse or directly. Yes, so the question from AS is uh, whether if the control valve is fail open or fail close, uh, then the control action, that is the reverse or direct. Yes, it indeed depends on the action of the valve. So if you have a process uh, which is if you have a controller which is reverse acting for a fail open valve, the moment you make it a fail close valve, it will become a direct acting. So it has a direct impact. So while deciding reverse or direct action, you have to make sure that what the controller output is going to be when so you have to see between u and y. If my output increases beyond set point, the controller input should increase or decrease. Now that automatically takes care of whether the valve is fail open or fail close. So I think these are all the questions. So again, I thank you for attending this session, and I hope you enjoy the rest of the course also. Stay safe. Thank you, and have a good evening.